So let's see how we can apply the derivative to some real world problems. This is a good problem right here, and these problems will explain to you a little bit more what the derivative really is. So I've got a bunch of them coming up here. Some of them are even in the homework. So let's look at this one. It says, so take a second to read the problem, and I will write this down. So we have h is 15t minus 1.86t squared. And what it says, what is the velocity of the rock after 2 seconds? So the velocity is the change in position, so the change in x with respect to time. And you can look at it like this. Whenever you have the xy plane, the velocity, so if this is x over here, I'm sorry, this is time, and this is the change in x, so how far something's gone, then the velocity, so I'm sorry, the position can be graphed like that. So this is position maybe. So we've gone up an amount x, so this is a positive change in x, and then over here would be a negative change in x here, so positive change in x here, negative change in x there, no change in x there. So it's going forward, and then it's going backwards over here. So forward here, backwards here, because the change in x backwards is going, it's decreasing. So the velocity is, think of velocity as distance. So remember, distance is rate times time. If you divide by time, you get time. If you divide by time, you get rate is distance over time. And so you can write this as x over t. So this distance here is the change in distance. This time here is the change in time. So the velocity really is the change in x over the change in time. So whenever you have height here, that is like your little x. It's just something's being thrown up and then it comes back down. So that's the change in x. So the velocity here will be the change in h with respect to time. So basically, you're just going to take the derivative here. So this would be 15 minus 1.86 times 2 times t, which is 15 minus 3.72 t. So this is your velocity function. All right, so what do they want us to find? What's the velocity after 2 seconds? So we just plug in 2, so v of 2, do this on my calculator, is 7.56. And that will be meters per second because it was in meters per second. All right, so then it says, what's the velocity when the height is 25 meters on its way up? So let's write down the height. So what it asks for is 25 meters on its way up. What's the velocity? So what we're going to have to do is find the time whenever the height is 25. So you just set this up by changing height to 25. And now this is just a quadratic in t. It's a quadratic. So I'm going to move everything over and then set it equal, and it will be equal to 0 at that point. And then when you use the quadratic formula on this, you get, so you'd get, what is it, t equals negative b plus or minus the square root of b squared, it's negative 15, but it doesn't matter, I'll square it anyway, minus 4ac 1.86 times 25 all over 2. And when you do this on a calculator, oops, this is times 1.86, it's 2a. And so on a calculator, this becomes 15 plus or minus square root of 39 all over 3.72. Now you're going to get two answers out of this. You're going to get 5.71 and 2.35. So what's happening here is the object is thrown up and then it comes right back down. There's no angle really, it comes right back down. And then at some point the height is 25. So, or the height is 25. So apparently at the first time it goes up, that's at 2.35 seconds. And at the second time it hits it, when it comes back down, it's at 5.71 seconds. So now what you do is, it says, what does it say in here? It says find the velocity at 25. So your velocity function was this right here, this 15 minus 3.72t. So you would plug that in. So the velocity at t is 15 minus 3.72t. So you'll do it at 5.71 and at 2.35. So what you get is negative 6.24 and positive 6.24. So it makes sense that the velocity is positive when you're going up at 2.35, and then the velocity is negative when you're going down at 5.71. So velocity is the change in the height with respect to time. So when the height is going down, when you're decreasing your height, this top one is negative. Times this one's always positive. The change in time is always positive. You can't go backwards in time, you don't go forward. So that's why the negative is the negative velocity is associated to when the object is going down. All right, so let's look at the next one. All right, it says find the average rate of change of the area of the circle with respect to its radius as it changes from these. So the average rate of change of a circle, the area of a circle, so the area of a circle is pi r squared. And so the average rate of change will be a2 minus a1 divided by r2 minus r1. So an area minus an area over the change in r. Okay, so basically this is the change in area, so delta A over delta r. And so from 2 to 3, so basically what you do here is you find the area at 3 minus the area at 2 divided by 3 minus 2. That's the radius. The radius is 2 to 3. It says as the radius changes from 2 to 3. So you just do that. So you just plug in pi r squared minus pi r squared over 1. So this would be, looks like it's going to be 5 pi, like that. All right, so then you do the same thing for 2 to 2.5 and 2 to 2.1. All right, so I did that real quick. So we did the first one, and I did the second one. So the area, the radius is going from 2.2 to 2.5. The radius is getting bigger. And then the last one, the radius is going from 2 to 2.1. We're finding the average rate of change. So we found that it went from 5 pi to 4.5 pi to 4.1 pi. So it's I'm sorry, that the radius is getting smaller, right? So it's going from 3 to 2, 2 to 2.5, and then 2 to 2.1. So what's happening here is you have a circle, and then you have the radius changing, and then from one radius to another. So another circle inside. So the circle inside has a radius of 2, and then the outer circle has a radius of 3. It has a radius of 3. And so you're getting smaller and smaller circles inside of that, and you're seeing what the average, it's not going to come out very good. Yeah, sorry. It should be, yeah, something like that. Anyway, it's getting smaller and smaller. And so that's the average rate of change. And so what did we go? We went from 5 pi to 4.5 pi to 4.1 pi. And so that's those quantities. And then find the instantaneous rate of change when r is 2. So it looks like it's tending toward 4 pi. There's something deeper here that I want to go over that's not really coming out in this problem like I'd like. If you have the average rate of, if you have the area of the circle is pi r squared, and then say you have, let's say you go from r2 to r1. So we go pi r2 squared, r2 quantity squared minus pi r1 quantity squared over, and then r2 minus r1. So this is the change in A over the change in R. If you look at the top, you can pull out a pi, and you get r2 squared minus r1 squared over r2 minus r1. And now you can factor the top into the difference of two squares. This is r2 plus r1 times r2 minus r1 over r2 minus r1. If you notice, these cancel. These two here cancel, and you're just left with pi times r2 plus r1. All right, so what I've drawn here is I've drawn two circles, one of radius 2 and one of radius 1. So this is r2, and then the green one is r1. All right, so now what I want to do is I want to draw a circle that's in between them. And this red circle is the average between the two. So the radius of the circle is right in between the two. So the radius of the red circle is r1 plus r2 divided by 2. Or you can write this as r2 plus r1. So r2 plus r1 divided by 2. So now if I multiply both sides by 2, I get 2r equals r2 plus r1. So what I'm going to do is I'm going to take that and I'm going to replace the r2 plus r1 with 2r. So we get pi times 2r, or 2 pi r. So this is the rate of change. So this is the rate of change of the area with respect to the radius. See how we got this? It was the rate of change of the area with respect to the radius. So we did all this math, we did this math, we did this math, did this math, and we ended up with this. And all I did was I said, okay, I'm going to rewrite this r2 plus r1 as 2r, where the red circle is the average of the two, has a radius which is the average of the two radii of the bigger circles. And so that ends up being 2 pi r. So what happens is when you start out with the area, which is pi r squared, the rate of change of the area with respect to the radius is the circumference, which is kind of cool. So to go a little further with this, if you just take the derivative of a with respect to r, you're going to get 2 pi r. So the area, the derivative of the area with respect to the radius is just the circumference. This is the circumference of a circle. And then if you want, this other problem here, where it says, it gives you the volume, it's the volume of a sphere. Volume of a sphere is 4/3 pi r cubed. It says, show that the rate of change of the volume with respect to its radius is equal to the surface area. The surface area of a sphere is 4 pi r squared. And you'll see that if you do dv dr, you'll get 4/3 times 3, pull this 3 down in front, pi, and then r squared, the 3's cancel, and you get 4 pi r squared. And so anytime you have a volume formula, the derivative of the volume with respect to the radius will give you the surface area.